How to design and measure a cryogenic bulk tank and piping supply system. The first and foremost information needed is the application details. This will require some basic details to successfully design a system. First, determine the type of tank service needed. Most will be liquid nitrogen, however other systems are available for most liquid use applications. Now that we know what product we will be using the system for, we need to focus on the use details. This would require us to survey the equipment list that this system will be providing product for. This list should include each piece of equipment with the following details: gas, liquid, or both required, flow requirements needed for operation per hour, desired operating pressures of both gas and liquid, daily operating times in hours, type and size of connections needed, and the weekly operating time in days per week. This will allow you to calculate both the required bulk tank size and the required pipeline header size along with the system equipment requirements. Some systems require use of both gas and liquid. This can be accomplished by using an APS unit. If the demand for liquid is less than 15 gallons per minute and the desired liquid pressure is between 20 and 80 psi, an APS unit can be used. This setup will allow the APS to control the low pressure liquid requirement and allows the bulk tank to supply the high pressure gas requirements. If the system is supplying liquid only and the pressure of the liquid is critical, the tank should be equipped with a vent to atmosphere regulator system. This system employs the use of two FRM style regulators, both set at the top side of the desired operating pressure. With one on each side of the dual relief tree, this ensures that the bulk tank pressure and liquid will not exceed the set value of the regulators. One basic rule of thumb on sizing bulk tanks is to use the amount of product to be used in a 3-week period as the size for the tank. An example would be for a system that is going to use 1,000 gallons per week, a proper size tank would be a 3,000 gallon tank. The last detail of the supply tank is the connections required. The optimum choice for a liquid withdrawal is a vacuum jacketed tank withdrawal. This allows the liquid connection to be totally frost free and limits the amount of product loss and gas phased flow generation in the system. Some of our testing has indicated that in nitrogen service, 1 foot of pipe not insulated and kept frost-free in a 70-degree environment will boil off nearly 40 gallons of liquid per 24-hour period. These non-insulated sections also will develop large loads of frost that can add weight to the pipe and cause failure. They can encapsulate valves and reliefs, rendering them inoperable. It will overwork cryo vent devices in the system. It can and will cause tank pressure problems. It does provide very poor quality liquid for our processes, and it also causes large product losses. And in the worst case, it can cause carbon steel outer vessel or support members to fail by cracking due to extremely cold temperatures. Now that we have covered the supply side of things, we can move to the layout side of things. If possible, gather as much data as you can. A plan view of the building is helpful if it is available. Communicate with the customer and end users to try to determine the most direct route for piping. Sometimes the easiest and most direct route may be across the roof of the building. Something to keep in mind when designing systems is that for every 10 feet of rise that the system increases from the tank supply point, an approximate 4 psi of supply pressure will be lost. Utilizing the sizing chart will help determine pipe sizes required. Typically, a main header supply is designed with runs off of the main header. These runs typically are sized down 1 diameter from the main header. Each branch from the run is typically also reduced 1 diameter from the run. Drops from the runs are typically reduced to 1/2 inch diameter. Each system design may have unique circumstances that may require using what is not typical. In system designs, safety relief valves must be incorporated. Anytime liquid can be trapped between two devices, a relief device is required. This includes end-use points. Cryo vents are not relief devices. Some cryo vents actually have a shutoff valve on the outlet, requiring them to be treated as a device requiring a relief valve. Manual valves, check valves, regulators, actuated valves, or any items that can stop flow or allow flow in only a specific direction typically will drive the need for a relief device to be incorporated. When designing the system, keep the installation of the system in mind. Clearly mark some key elevations on the drawings, along with possibly general install material notes. Pictures can also be very valuable. Keep in mind also any limiting factors such as stairways, hallways, elevators, and other obstructions that could cause issues with the moving in place and installation of the pipe. If wall penetrations are made, it is valuable to mark these locations with a permanent marker to allow the installation team to know where the entrance point or pass-through points were designed. Some design rules of thumbs are: recommended system slopes should utilize 1 inch slope per 10 feet. This slope should always run uphill to the cryo vent. Traps should never be generated anywhere in the system. Even sagging flex line or improperly supported pipe can cause a trap area. Hangers and supports should be spaced at 10 feet or less when installing the system. One cryo vent should be planned for every 100 feet of pipe run. Multiple types of cryo vent configurations are available. The standard cryo vent has a non-insulated exhaust and will create a frost area at the exhaust. This must be considered when designing the system. Cryo vents with a bayonet exhaust will allow use without frost. Two means exist for the exhaust of this type of cryo vent. One is to use a cryo vent exhaust heater. This heats the exhausting gas to keep the exhaust frost-free. This should not be used in confined spaces. The second option is to run the exhaust outside using VJ Flex. On drops near the use points, without vacuum jacketed valves, internal traps can be used to stop frosting of non-VJ valves during non-use times. In this portion of the video, we're going to talk about how to measure the pipe sections that are going to be needed for a specific job. This is something that can be supplied by chart. It is isometric drawing paper. It'll allow you to take your measurements and put the design of each section of pipe on this paper so it can be drawn up, designed, and manufactured at chart. The first section we'll measure here is BS1, and I'll explain how these measurements take place. So you see that there's a beginning point on section BS1, and it's clearly labeled, says 2 bulk tank VJ. That would be this piece right here, up to here. This is our bayonet connection. Then I've also labeled 1 1/2 inch male bayonet, because that's what will plug into the existing tank and vacuum jacketed valve and line that is on the tank. These isometric drawings are typically drawn so you have a main header and then all of the appendages is coming off of that main header and are drawn in a view where they make sense of how the section is actually laid out. So that said, within this we have an overall measurement of the length of the section from the male bayonet that's going to connect to the bulk tank, which goes over to this part right here, which is labeled 2VS2, which will be the second section we would measure and design. It also states 1.5 inch male bayonet. So a measurement like that is an overall measurement from our bayonet connection on one end to our bayonet connection on the other end. That dimension is then recorded as an overall length from bayonet to bayonet. You'll also see in here that we've incorporated flex for the ability to be able to hook up to the tank. That flex is labeled 4-foot flex, and you want to make sure you clarify what that flex needs to be. This specific one we say inner and outer braid, meaning that it has inner braid on the inside flex and it has outer braid to protect the outside flex. That is measured just as this, that we have a 4-foot piece of flex in the line. Then you'll see that we make some direction changes where we go up and over for an auxiliary line. Critically important that when that's done, you label what that T section is. You'll see on this one I've labeled it 1 1/2 inch by 1 1/2 inch by 1 inch T. So they know that this is a pipe size change, that the header is 1 1/2 inch, and that once we begin the rise up here, we reduce that down to a 1 inch section. Same thing happens here where we take a 90 and we come over to this riser where we're going to put a relief valve. You see that it's clearly labeled relief valve with a 1/2 inch MPT connection on it. You also see the denotion that we have 1 inch by 1 inch by a 1/2 inch T, meaning that the header is 1 inch and we're going to come up as a 1/2 inch to supply the relief valve. You also see that I've labeled distance in all these things for heights and overall lengths again, so we understand exactly what needs to be built to come to that. You can look at the end here, you see that it's labeled 1 inch MPT. That means there's going to be a 1 inch pipe thread on the end of this section. If the need for a valve is required there that you expect chart to supply, there should be a notation added to this to say 1 inch non-insulated supply valve or whatever is required on the end of that section or expected on the end of that section. You'll also see that I labeled on the drawing here VS1. So this is the section I drew, the first section. This system obviously has many sections, so it would probably take quite a few pages to put it all together, but you should be able to always link these drawings by, again, the starting point here should be labeled what it is. It says 2 bulk tank VJ. At the end of this section it says 2VS2. If we went to the next section it would say 2VS1 on this side, and on this side it would say 2VS3. So it denotes where that section is actually going in the system design. Another thing, all of these systems have vacuum pump out ports that are put on the section. If it is not detailed on the drawing, the draft person who puts this together will choose where to put that pump out. So if we have a specific place we need to have that pump out, we absolutely should put a label on the drawing and draw a pump out in here, and we should call it a pump out. And then we should put a dimension on the drawing so that it's understood that if it needs to be 7 inches, that it's understood that we put 7 inches here, so they know, okay, that's where that pump out needs to be. This can be very critical in areas where it needs to go through walls, or if there's obstructions where the pipe is very tight to something, that the pump out needs to be in a specific spot. In other words, this pump out could be anywhere on this entire section. It could be here, it could be put in here, it could be put virtually anywhere, but again, it needs to be labeled on the drawing, so when the draftsman draws this up, they understand that that is a critical point of where that pump out needs to be.